The last set of fundamental identities I want to look at is the even and odd identities. So we've already discussed the fact that sine is an odd function. We can see that from the graph. This graph has rotational symmetry, or symmetry about the origin. And of course, if it's odd, what that means is that the opposite input gives us the opposite output. Cosine, on the other hand, is even. This graph is symmetric about the y-axis. The left side is just a mirror image of the right side. And what that means is that the opposite input gives me exactly the same output. So these identities allow me to simplify things so that if there's a negative sign in the input to my trig function, I can make it so that there's no negative sign on the input. If it's a sine, since that's odd, I write the negative sign in front. And if it's cosine, that's even nicer. Since that's even, the negative sign just becomes irrelevant. All right. Now it turns out that all 6 trig functions are either even or odd. And what I want to do is try to figure out what the other ones are. And I'm going to do that by using either the quotient or the reciprocal identities. So, for example, let's suppose I want to figure out about tangent. Looking at tangent, if I plug in the opposite of x, what does that give me? Does that give me the same thing as tangent of x, in which case it would be even? Or does that give me the opposite of tangent of x, in which case it would be odd? Now, there are certainly functions that are neither even nor odd, but none of the 6 trig functions falls into that category. They're all either even or odd. So what I'm going to do is say, I can use my quotient identity. I can write tangent in terms of sine and cosine. So tangent of negative x is the same as sine of negative x over cosine of negative x. Okay? That's just using the quotient identity that tangent of anything is sine of that thing over cosine of that thing. But now I can use the fact that I know that sine is an odd function. So the top of this fraction becomes negative sine x. And cosine's an even function, so the bottom of the fraction just becomes cosine of x. And then, when I have a negative sign in a fraction, I can write that one of 3 places. I can associate the negative sign with the top of the fraction. I could bump it to the bottom and associate it with the bottom of the fraction. Or I can write it in front. I can say, this just makes that fraction the opposite of this. But oh my goodness, that's the opposite of tangent of x. So that tells me that tangent is also odd. So that tangent of the opposite input is the opposite of tangent of x. Okay. It's kind of interesting with this fraction. I had one function that was odd on top and one function that was even on bottom. That introduced one negative sign, so that gave me the opposite output. Okay, what I would like you to do is classify the remaining 3 trig functions. So the 3 that are defined in terms of reciprocals. So I want you to take a look at secant of negative x and cosecant of negative x and cotangent of, I should probably be saying the opposite of x. I've already told you that you're either going to get the same thing as the trig function at x or the exact opposite. Again, that's not true for all functions, but that is true for all 6 trig functions. So I want you to see if you can use the quotient and the reciprocal identities to figure out whether these functions are even or odd. So pause the video, give that a shot. So in working with secant, I'm going to use my reciprocal identity. Secant of something is just the reciprocal of cosine of that thing. But then I know that cosine is even, so this is the same as just 1 over cosine of x, which is just secant of x. So with secant, the opposite input gives me exactly the same output. Secant is even. We actually saw this when we were graphing some transformations of secant and cosecant, we saw that if we had a negative sign in the argument of the trig function, we were able to use the fact that secant, because it was the reciprocal of cosine, was actually even. This is just how we would go about proving that algebraically. For cosecant, I'm also going to use a quotient identity. I'm going to say cosecant is the reciprocal of sine. So cosecant of the opposite of x is the reciprocal of sine of the opposite of x. But sine is odd. So that's 1 over the opposite of sine of x. Notice here the negative sign is being associated with the bottom of the fraction. But again, I can just write that in front of the entire fraction and say this is the opposite of 1 over sine x. But that's the opposite of cosecant of x. So cosecant, let's write that out, cosecant is odd. So this shows us that if a function is even, its reciprocal is even. And if a function is odd, its reciprocal is odd. This is just 2 examples of that more general fact. Now for cotangent, I'm going to use the quotient identity. I'm going to say that's cosine of the opposite of x over sine of the opposite of x. If I wanted to, I could have used the reciprocal identity. I could have said that's the reciprocal of tangent, because I've now figured out that tangent is odd. I'm going to use this quotient identity instead. Cosine is even, so cosine of the opposite of x is cosine of x. Sine is odd, so sine of the opposite of x is the opposite of sine of x. Here again, the negative sign is associated with the bottom of the fraction, but I can pull that out in front and just say that's the opposite of cosine x over sine x. So that's the opposite of cotangent of x. So that tells me that cotangent is odd. So actually 4 of the trig functions are odd. Sine and its reciprocal cosecant are odd, and tangent and cotangent are also both odd. So the 2 that are even are cosine and its reciprocal secant.